Good evening. It's my pleasure to introduce Laura Britton. I don't know if Laura needs much introduction. Laura's a visiting faculty this semester, teaching one of the fourth-year option studios with McKenna. She's an architect, an accomplished author, and a prominent voice in the field of mass timber. As an associate at Shigeru Ban, Laura's played a pivotal role in a range of innovative projects, including the Kentucky Owl Park Bourbon Distillery, the Terrace House Residential Tower, and the adaptive reuse of the historic cast iron house. Her expertise extends beyond project design. Laura is the co-editor and author of the book, The Shigeru Ban, Timber in Architecture, which we're going to hear a lot about this evening. It's a comprehensive exploration of 45 mass timber projects that highlight the complexities and advantages of working and building with timber. As an advocate for environmentally responsible design, Laura has shaped her insights on decarbonization and interdisciplinary approaches at numerous conferences, including the AIA International Spring Conference, as well as the Skyscraper Museum here in New York. With a Bachelor of Arts from Yale and a master's degree in architecture from Princeton, where I think I originally met you, she received notable honors. Laura continues to inspire and lead the conversation on the future of sustainable architecture. So that's a brief introduction, and I hope afterwards we'll engage in a conversation about the book. So please join me in welcoming Laura.
Thank you so much, everyone, for coming out this evening. And I'd like to extend great thanks to Hayley, as well as McKenna for having me at Cooper this semester. It's an honor to be here with you all. So as Hayley mentioned, I'm an associate at Shigeru Ban Architects. I was drawn to Shigeru's work because of his earnest and tireless pursuit of environmental and humanitarian conscious architecture, as well as his structural and material innovations. So since I joined the firm in 2015, I've predominantly worked on timber and mass timber projects. I hope that everybody had the opportunity to catch Shigeru's lecture 2 weeks ago. He covered an amazing 35 projects in 45 minutes. We're going to go a bit slower this evening, take a deeper dive into timber projects, and concentrate on how they actually come to fruition, which is through great interdisciplinary collaboration. Before then, I wanted to just give a quick preview of the work that McKenna and my studio has been doing. So we are teaching a fourth-year urbanism studio that's rooted in the same principles as this talk. And the prompt is to design a museum of sound, which is very open to interpretation. The primary medium for this is wood. We have 2 sites. The first is Cape Town, South Africa, and the second is Poughkeepsie, and each site has half of the students. So our students are considering the ecological impact of their material and product choices, from regional species availability to where wood products are manufactured, which ultimately influences the carbon footprint of the project. We recently completed timber precedent analysis, which considered a diverse range of projects from where timber plays a central role, but not necessarily a structural one. For example, starting with the Ise Shrine, here Aaliyah's study reframes building maintenance as a cultural ritual of building stewardship. We're also studying reclaimed wood, learning from vernacular construction, drawing fabrication techniques from unusual sources like steam bending from boat construction. We're questioning how structural member size can convey lightness, and the implications of reinterpreting concrete structures in timber. The studio is also looking into hybrid solutions because we aren't timber purists. Wood is not always the answer. So here we're considering the carbon impact of using local and regionally available materials, including both timber and rammed earth. And lastly, we're considering material waste inherent in our conventional approaches to structural design and how short plant fibers and natural binders create alternative building materials. This is particularly useful for irregular growth patterns in trees like the ones near our Cape Town site. So before we dive into SBA projects this evening, I always like to start with the question, why wood? So we'll start with a quick primer. Wood is a versatile natural material with diverse structural possibilities. It's sustainable and renewable and can often be locally sourced. With off-site construction, timber construction sites are typically cleaner and safer, and construction schedules are shorter. You might be familiar with the term biophilia. Buildings with visible natural materials are noted for their positive psychological effects, promoting health, happiness, and thriving. Now more than ever, it's imperative that everyone, from students and architects to builders, clients, and even the general public, recognize that construction impacts the environment. Issues of waste, permanence, and material selection are crucial considerations in a holistically sustainable approach to design and construction. You've probably all heard the statistics. Buildings account for nearly 40% of the world's carbon emissions, with 11% due to construction alone. In terms of embodied carbon, wood far outperforms alternative structural materials such as steel and concrete. And this is a large reason why many architects advocate for the use of wood. But it's reasonable to understand concerns about wood. First, what about deforestation? Contrary to popular misconceptions, the use of sustainably sourced wood from small diameter trees actually promotes forest health, making them more resilient and fire tolerant. Next, isn't wood expensive? Many people think only about the unit cost of wood, but in actuality, reductions in on-site labor and construction duration yield considerable cost savings. Next, is it safe? Won't it burn? Yes, all materials burn. But fortunately, sufficiently thick wood actually burns at a slow and predictable rate. And like any structural material, factors of safety are required. At the bottom left, you can see the results of fire testing. Oversizing the structure allows for a sacrificial outer layer that can char without compromising the structural integrity of the member. This charring acts as a protective layer, slowing the rate of combustion and insulating the core of wood. Finally, will it last? The oldest timber structure in the world is the Horyuji Temple in Japan, which is more than 1,300 years old. It still stands today in part because of its strong and durable materials, robust structure, and precise detailing, but also because it's of great cultural significance. As Shigeru often notes, if a building is loved, it becomes permanent. This concept transcends materiality. Buildings that are meaningful to their communities are cared for, and that's actually the most environmentally responsible approach to create architecture that will endure for generations. But wood isn't always the answer. Each of the points listed here could be a deterrent to building in wood, or it could be the starting point for an innovative response in the face of constraint. For example, what if the building code doesn't allow mass timber construction? Ironically, Shigeru has found that some of the most restrictive building codes in the world are in urban centers in Japan. The misconception in this case is that mass timber is not safe. But in actuality, building code hasn't always caught up to the realities demonstrated by rigorous testing. Shigeru grappled with this over 2 decades ago when he was commissioned to design a new office and showroom for a dental company. Since long-span timber structures were not allowed, he opted to work with steel for its strength and its ability to span long distance. Steel typically requires a fireproofing layer, which is known as encapsulation. This prevents structural damage in case of a fire. So typically you use a finished grade material to improve the appearance after this. Subverting the logic, Shigeru demonstrated to officials that wood could in fact be used to fireproof the steel. Fire resistance tests demonstrated that 50 millimeters of wood, or about 2 inches, adequately addressed the building's 1-hour fire requirement. Therefore, 2 layers of particle board with a thin plywood finish were used to encapsulate the steel. So despite not being a timber structure, it still retains the warm aesthetic of wood. Madak Nagoya is a more recent example, and you may recognize this from Shigeru's lecture. Here, the client, again, was seeking the benefits of biophilia for his staff. This 8-story building is also located in a Japanese city. So to satisfy the building code and retain the warm wooden interior, a unique hybrid approach was devised. In the diagram at the right, you can see that a box was constructed from wood, rebar was inserted, it was filled with concrete, and then the wood formwork was actually left in place. So this formwork is made out of CLT, which is cross-laminated timber, and that's a type of mass timber. The use of permanent formwork has many benefits, most notably the biophilic benefits of wood, a shortened construction schedule, reduced carbon footprint, and not needing additional finish materials. Returning to our list, the availability of materials and skilled labor could also be seen as deterrents. Simply selecting wood does not make it a sustainable choice. For example, spruce from Switzerland, which is very high quality wood, would be quite irresponsible in Southern California. But sometimes the topic of local materials is less related to regional wood species and more a matter of which building products are locally available. In one of SBA's earliest projects, Shigeru was commissioned to design a house on a remote wooded hillside, which posed construction challenges regarding site access. He designed prefabricated plywood furniture units as the primary building structure. So instead of walls and columns, cabinets and bookshelves made up the structure of the building. This allowed for off-site construction, reduced construction time and material waste, and no need for on-site skilled labor, yielding both cost savings and a higher quality building. So here you can see each of the 33 plywood furniture units, which weighed about 175 pounds each, could easily be maneuvered into place by 2 people. So as we continue to look through this list, hopefully you come to the realization that these potential pitfalls are always opportunities to think creatively and materially and to engage with structural engineers, fabricators, material testing facilities, code officials, among others. So returning to the question of why wood, this is something that Shigeru Ban Architects has been asked nearly every time we've presented in the past decade, and it becomes almost a preamble to our concept presentations. So about 5 years ago, I proposed putting this together in a book alongside all of our firm's works in timber to both serve as a timber monograph, but also a primer on building with wood. Much like a building, a book is not a solitary endeavor. So this was a global and interdisciplinary effort involving structural engineers, fabricators, and our staff from all 3 offices, Tokyo, Paris, and New York. The book begins with 3 guest essays to contextualize the importance of the subject of timber in architecture. There's a foreword by environmentalist and entrepreneur Paul Hawken, and then Shigeru's own essay, Why I Love Wood in Architecture. Next, we have Hermann Blumer's recounting of his trajectory from life as a humble carpenter to an international timber engineer. And this is followed by the body of the book, which presents 45 works from concept through construction, demonstrating the merits and challenges of working with wood. Projects range in scale, budget, and program, from prefabricated plywood houses to parametrically modeled glulam grid shells, showing the spectrum of what wood can do. The projects are illustrated through photographs, technical drawings, and the documentation of the construction process as well. So whereas steel and concrete can easily be formed into any number of shapes, you really need to understand the material properties of wood to optimize its structural form. By leaving timber unencapsulated, this allows the beauty of the material to be expressed and to show wood as both structure and finish. This is a materially authentic approach, expressing the beauty of rational structural forms. But to do this, we need to collaborate. From the outset, we engage a core team of engineers, including structural engineers, fabricators, and builders, seeing the real-world constraints as possibilities. Shigeru has great respect for his collaborators, and his introductory essay is dedicated to his close working relationship with 3 renowned structural engineers, first Gengo Matsui, then Frei Otto, who he noted is also an architect, and lastly, Hermann Blumer. Gengo Matsui helped to bring Shigeru's early paper tube concepts to fruition, advancing beyond simple upright columns. With Frei Otto, Shigeru delved into form finding. So here you can see the influence of Otto's Mannheim multi-hall on Shigeru's paper tube pavilion. And lastly, we have Hermann Blumer, who also wrote an essay for the book. He began his career as a carpenter before pursuing a PhD in structural engineering in 1969. But at the time, his focus on wood was looked down on since his colleagues didn't think this was complex enough to warrant doctoral study. But Hermann persisted and became a pioneer of digital fabrication, later designing the first fully automated CNC machine. Here you can see the breadth of his understanding of structure, materiality, and craft in the Nine Bridges Golf Clubhouse. Projects in the book are arranged thematically by structural typology rather than chronologically. This organization reveals the influence of budget, code requirements, regional tree species, access to skilled labor, and local fabrication capabilities. So for the remainder of the presentation, we'll be concentrating on mass timber structures, but first, again, a bit of a primer. So in contrast to dimensional lumber, which is composed of a single piece of wood cut from a solid log, Engineered wood is a manufactured wood product. It's a composite composed of wood veneers, strands, or particles, plus an adhesive. Graduating in size, mass timber is also an engineered wood product composed of wood from smaller diameter trees, but this time bound together by adhesives, nails, or dowels to create larger structural members. This has two primary advantages. First, it doesn't take advantage of old growth trees, and second, mass timber is inherently stronger than comparably sized solid wood. This is because it's a composite, so it is a standardized product with predictable strength characteristics. Common examples of mass timber include glulam and cross-laminated timber, as well as LVL, mass plywood panel, nail laminated timber, and dowel laminated timber. On the left, you can see an example of heavy timber, which is solid wood from old growth trees. And on the right, you may be able to see some joint lines parallel to the structural members. Those beams are made of mass timber. So as you approach a mass timber project, here are 10 key points to keep in mind. These points are applicable regardless of the complexity of a project. So first, we have to ask, why wood? Is it even the right material for the job? Oftentimes, a hybrid solution is the best approach. Next, we review the building code to understand what you can do in a given jurisdiction and establish the building type and fire rating. From here, we can establish the structural grid. So this means considering spans and member sizing in relation to vibration and deflection. Once the grid is established, we can consider the MEP strategy. Do building systems bypass the structure or pass right through it? And lastly, how do we optimize the volume of wood to both minimize waste and erection time on site? Now we can think ahead to constructability. Ideally, you want to meet with your mass timber suppliers and fabricators at the outset of the project. Which species of wood would you use? In the Pacific Northwest, you're more likely to think of a spruce pine fir, but in the South, perhaps southern yellow pine. You'll consider also the manufacturers and fabricators' geographic proximity to one another and your project site. As you consider connections and tolerances, you think again about your partner's fabrication equipment and how this project will come together. With all of this in mind, your partner's capabilities and limitations inform the design process. So we don't work in a vacuum as architects and then go to our structural engineers and fabricators. You bring them in right at the beginning for these complex projects. You simply can't fabricate projects the same way in New York and Switzerland nowadays. Lastly, as you begin to outline the erection strategy, which we often do in SD, we start to think about how many truckloads it takes to take your material to the site and how that impacts both cost and schedule. So for the remainder of the talk, we'll be focusing on mass timber buildings in 3 structural typologies: space frames, tree columns, and grid shells. The Aspen Art Museum was designed as a unique but contextual building. Its woven wood and paper composite facade is evocative of the color and rhythm of Aspen's historic red brick buildings, but the porous screen facilitates views into the museum and out towards the mountains. Here you can see 2 views of the Grand Stair, which is an indoor-outdoor interstitial space behind the woven screen. Similar to the experience of skiing, the museum was designed to be circulated from the top down. Visitors first ascend via the Grand Stair and then arrive at the rooftop plaza before descending into the protected galleries below. Shigeru believes that the context is as beautiful as the art, so it was important to highlight stunning views of nature from Aspen's only free rooftop. Here you can see the timber space frame structure, which extends over the rooftop plaza and into the cafe. The building is arranged according to what we call the thermos principle, which was developed alongside Transsolar. Here, climate-sensitive galleries are concentrated at the heart of the building and are surrounded by less climate-sensitive spaces, such as lobbies, hallways, stairs, and offices. This minimizes temperature and humidity fluctuations in the galleries and allows perimeter zones to take advantage of the visual and physical connections to the outdoors. In the left 2 images, you can see Shigeru's hallmark paper tube furnishings, which aren't too humble for a high-end art museum. So for comparison, on the left, we have Shigeru's initial concept sketch, and on the right, a digital model used for fabrication. So those are the actual shop drawings. This project began with a structural and material concept. But it isn't as simple as starting with a clear structural idea. This project went through 5 iterations to determine how to fabricate the structure. So initial studies began with vacuum forming the timber and then CNC routing it, but this was far too expensive. Ultimately, the webs were cut 2-dimensionally from custom Baltic birch plywood, which is more commonly used for furniture. And this had never been done before, so here you can see extensive testing was required to demonstrate the strength of the material in this application. In order to come up with this fabrication approach, our structural engineers and fabricators co-located and essentially performed a workshop over the course of a few days. So here you're seeing a mock-up of the timber structure being built. For the final design, spruce, which is a very common softwood, was used for the cords, and birch plywood for the webs. Using a hardwood in this application allowed for stronger connections and reduced member sizes. The plywood came in 12-foot lengths, which were half-lapped as scarf joints. And in the upper left, you can see the 2D webs in Spearhead's shop. Timber components were fabricated and shipped to the site in the longest possible transportable lengths, which ultimately minimized on-site labor and construction duration. You may notice that this is a bit of an unusual approach to a space frame because the webs here are curved. This allows for sufficient wood-to-wood contact so that the webs could be connected directly to the cords with just diagonally oriented wood screws. As a result, there are no exposed metal connections. The structure here was developed in conjunction with Herman Bloomer from Creation Holtz, Greg Kingsley from KLNA, and fabricator erectors Spearhead. Like the Aspen Art Museum, here the Triangle House also features a space frame roof, but it's a much smaller scale. This building is for an 8-person office with a private residence above. And while the lower floors have a concrete structure to economically support the load of the building, the space frame roof allows for an open living space with few columns on the upper level. Despite being nearly 1 meter deep, there's plenty of daylight in this space frame. The wooden structure is made of European pine, which was selected because it's economical and readily available. At each node, up to 9 members intersect, which is particularly complex. And like at Aspen, hardwood joints were initially considered, but this wasn't possible due to the particulars of Japanese building code. So instead, after a series of, again, 5 iterations, an interlocking wood joint with steel plates was ultimately resolved for this project, which for us demonstrates that regardless of challenging conditions, there's always a design solution. Now moving on to grid shells. Hopefully you remember Shigeru's discussion of the Centre Pompidou Metz. We're going to dive into the backstory a little bit. So this is perhaps Shigeru Ban's most iconic building and one of the most well-known mass timber structures in the world. And though it might be hard to imagine today, the client initially suggested switching to a steel structure for this roof structure. In 2003, the Centre Pompidou had hosted the initial competition to design a new museum outside of Paris. The intent was to show more of their 120,000 work collection, as well as larger works that wouldn't fit within the Centre Pompidou's 18-foot ceilings. Given the architectural significance of this, Shigeru saw the opportunity to build an unprecedented structure. The museum was designed as an open pavilion in the park and consists of a timber grid shell supported from a 250-foot tall steel core tower. Despite its sculptural image, it's a simple hexagon in plan, which is symbolic of the shape of France. And as Shigeru mentioned, the 3 gallery tubes are oriented towards local landmarks. So here you can see the Metz Cathedral. For the iconic roof, Shigeru drew inspiration from 2 seemingly unrelated sources. The first was cable net roofs designed by Frei Otto, which have a separate cable structure and wood enclosure. And the second is the self-supported woven structure of traditional Chinese hats, which made Shigeru question the necessity of the cable net. In a typical triangulated grid, you'd have 6 members intersecting at a point. This yields a very complex and expensive joint. But here you can see the influence of the woven Chinese hat. By offsetting the grid, only 4 members meet at a single point. This is the ingenuity of Metz. The story of this building's structural resolution is really fantastic. After the initial team of engineers proposed a hybrid structure, followed by a solid wood structure that was twice the roof's budget, the client then asked Shigeru to change the roof to steel. But Shigeru wasn't deterred, so he went to Germany to consult with timber engineers and fabricators. At the airport, he was greeted by a Swiss man who he thought was his taxi driver, and he had a very pleasant conversation on his way to visit his engineers. But in fact, that was Hermann Blumer. The two sides of the story are beautifully recounted in the intro essays to the book. Shigeru described his conundrum, and Hermann said, "No problem, I will have a solution for you in 2 weeks, along with a cost estimate." If you read Hermann's side of the story, he said he had absolutely no idea. And so then and every time since when Shigeru has given him a complex problem, he goes off to the mountains, thinks a bit, comes down, rhino models it himself, and he's in his 80s, and then comes back with a solution. This is still how we work today, and this project was the start of that relationship. Independently, Shigeru and Hermann each realized that they needed to not only simplify the grid in 2 dimensions, but also to offset the depth of converging members so that they bypass one another at the nodes. So just to visualize, instead of your beams coming together this way, they bypass one another. The result that you have here is that the connections could be made by a simple pin, so no expensive fabrication of timber joints. In this configuration, each beam now acts as a veer and deal truss. The beams are made of spruce, which is a softwood, and the connections are made out of beech, which is a hardwood. The beech hardwoods take on the high stresses of each joint. The double curvature of the roof takes advantage of digital fabrication, which was pioneered by Hermann Blumer. Now moving on to tree columns. At the same time as Metz, Shigeru was commissioned to develop the Nine Bridges Golf Clubhouse, which is also a grid shell, but noticeably different in form. The building is essentially a box with a flat roof, but it's supported by 3-story tall tree columns. Each column is composed of 12 timber members arranged radially. You'll notice that the roof structure bears the same hexagon and triangular grid structure as Metz. However, the higher density of this slender framework allows the roof to read as a continuous undulating surface instead of a grid of discrete beams. The tree columns are constructed from 3-dimensionally curved German spruce glulam, which takes advantage of the direction of the wood grain to create a structurally efficient form. Unlike Metz, here all members do occupy the same plane, so they're not to accept one another in half-lap joints. The images to the right show that the roof structure was assembled and pre-assembled from prefabricated modules that were lifted into place by a crane. 10 years later, Shigeru was asked to complete another structure by the same client. Here, it was a media engagement center at the golf club. And so in order to keep the space quiet, Shigeru submerged this event space. He also proposed adapting the original tree column structure to provide a light and airy feel despite the building now being subterranean. You might notice that this is quite hefty compared to the prior building. That was because there was a change in Korean building code over the course of the decade from one project to the next. Secondly, instead of having the twisting 3-dimensional curvature of the Nine Bridges Golf Clubhouse, here the wood members curve in only 2 directions, which allowed the project to be fabricated in Korea rather than imported from Switzerland. And third, Shigeru never wants to repeat a concept exactly. He likes to have more complex projects over time. So he added a reflecting pool to the top of the structure and integrated trees right into the column structure. So you can see in the diagram at the right, the trees are centered on each column, and that kind of silver looking basin at the top of the columns is actually the tree planter. Here again, Shigeru adapted the tree column form, this time for a more modest project. Yufu Info is a tourist information center that sits adjacent to an existing rail station by Isozaki. This building is an entirely timber structure, but since it was publicly funded, the structure had to be expressive yet cost-effective. Japan also has more limited timber fabrication capabilities than countries like Switzerland, so the curves here also only curve in 2 dimensions, similar to the previous project. Each tree column consists of only 4 members, which is offset by their robust size and allows for fewer total columns and beams, and therefore fewer connections. These 3 projects highlight how a similar structural system can be differently impacted by budget, code requirements, and access to skilled labor, and also how collaboration with structural engineers and fabricators plays a large role in navigating these conditions. Returning to a purer form of grid shells, the last project that we're going to look at, the last built project, is the Swatch Omega campus. At over 500,000 square feet, this is among the largest mass timber building projects in the world. The campus integrates 3 new mass timber buildings into a historic watchmaking facility in Biel, Switzerland. On the left, there's the Omega factory. On the right, the Swatch headquarters, and between the two is Cité du Temps, which is the Swatch Omega Museum. The buildings share a design language reflected through the unified brands of Swatch and Omega, while expressing each building's individuality through contrasting structural form. We'll take a quick look at the rectilinear buildings, but focus on the grid shell. The Omega factory was built first. Omega is known for being the timekeeper for the Olympics and NASA, so it was fitting to have a clean rectilinear form that reflects Swiss standards for precision. The building is a post and beam structure with a rigid concrete core flanked by timber-framed watchmaking workshops. Working conditions were a primary factor for the building's design. Most notably, literal cleanliness is important here. The Omega factory is the first building in the world to achieve clean room standards in a mass timber structure. This certification was important for the sake of craftsmanship as well as employee health, since the workplace had to be evenly lit and dust-free with minimized vibrations. Since mass timber structures are known to be light, which is usually a benefit, it means that you can have a lighter concrete foundation as well. Here, it's a bit of a problem. You don't want your floors to vibrate when you're doing careful watch building work. So a concrete topping was added to increase the weight of the CLT structure. In contrast to the maturity of the Omega building, here the Swatch brand is represented in a playful, innovative, and provocative design. And though its serpentine form and facade design appear rather unrestrained, each is in response to practical design constraints ranging from code and zoning setbacks to material properties and building services. The sculptural grid shell covers 4 office floors and connected via 3 concrete cores. The timber structure is composed of a 7-foot grid of interlocking timber beams that seamlessly transition from wall to roof structure, and that allows the office space below to be open and flexible, fostering collaboration. The Swatch headquarters was designed in a truly contemporary manner without traditional construction documents. Instead, a parametric digital model accounted for all 7,700 timber components with a precision of 0.1 millimeters. This allowed the wood to fit together perfectly on site like puzzle pieces. A more typical building project might expect errors to impact up to 15% of the parts delivered to site, but this complex grid shell had only a 0.11% error rate, meaning only 72 of the 62,792 prefabricated roof elements had an error. This is a testament to the truly interdisciplinary and collaborative nature of the design process. Here again, we worked with Hermann Blumer from Creation Holtz and digital facilitators Design to Production, who created a digital fabrication model to resolve potential conflicts between the structure and building services. This dynamic team has worked together for nearly 2 decades since the Centre Pompidou Metz project. Here you can see the building envelope integrating structure, building services, and the facade. Since the maximum footprint of the building was fixed due to site constraints, an unnecessarily thick envelope would have reduced the building's usable floor area. So to resolve this, Shigeru drew inspiration from the original Swatch watch, which integrated components directly into its manufactured plastic case. This reduced both the cost and the thickness of the watch. Shigeru's approach was similar. So instead of having discrete layers of structure, building services, and facade, here he integrated the 3. The facade nests into the structure, and building services pass through it. Prefabricated openings were tailor-made to the size of electrical cables, sprinkler pipes, and cooling pipes, with the cutouts staggered to be mindful of the wood grain so that the structure wouldn't be weakened. The 120,000 square foot roof surface has 2,800 apertures in total, arranged in a spirited pattern of ETFE cushions, CLT panels, PV panels, and acoustical absorption panels. The Swatch grid shell reaches over a festival street and sits atop its neighboring building, Cité du Temps. This museum and conference center acts as an interface between the Swatch and Omega brands. It incorporates the architectural language of its neighboring buildings with playful concrete arches at its base, which is a nod to the Swatch building, and a rectilinear timber structure for the 2nd through 5th floors. The mansard roof is evocative of the campus's historic buildings. The Omega building has a concrete core and topping slab, but CJ du Temple is an entirely timber structure above the ground floor with glulam columns and beams and CLT floor slabs and core panels. This is an outwardly simple building, but its complex details its complex interfaces require more attention to detail. So not only are there timber and concrete structural systems, but the building is literally intersecting with its neighbors on both sides. Despite being such an enormous project, collectively, these 3 buildings were constructed from 160,000 cubic feet of certified Swiss timber. This is kind of a hard number to wrap your head around, but considering the growth rate of Swiss forests, it would only take 10 hours to regrow this quantity of wood domestically. That accounts for 0.1% of Switzerland's annual timber production. So hopefully that addresses any concerns about deforestation. To conclude, here's a look at one of our projects in the US. Kentucky Owl Park is a 500,000 square foot distillery in Bardstown, Kentucky, located in a 420-acre reclaimed limestone quarry. The distillery is situated on a peninsula at the center of the site, surrounded by production buildings, a bottling center, a craft cooperage, and rick houses, as well as a visitor center and train station. In the visitor center, we drew inspiration from the structure of a bourbon barrel itself. The dendriform columns are a combination of timber and steel, which is evocative of the wood staves and steel hoops of a bourbon barrel. Here you can see the 3 pyramids of the distillery. The adjacent lake water is used to make the bourbon. In the first pyramid, visitors gather for tours and are educated about the bourbon making process. The second pyramid, which is shown at the right, is where distillation takes place. The shape of the pyramid actually comes from Shigeru's pragmatic idea to efficiently accommodate the 60-foot tall column still at the center of the building while minimizing the overall volume of the building. And in the last pyramid, bourbon is barreled in preparation for aging. The roof structure here may seem similar because it's an evolution of the Aspen Art Museum's wooden space frame. So with each project, as we build on our past structural and material studies, we can increase in complexity. Here, the complexity comes from both the angle of the space frame and how the 4 faces of the pyramid meet. To do this, we once again teamed up with structural engineers from Creation Holtz and KLNA, digital facilitators Design to Production, and fabricators at Spearhead. This sheet is a reference geometry drawing from our schematic design set. In the diagram at the left, green represents the outer face of glass, blue is the top face of the wooden cords, and red is the bottom face of the wooden cords. So in actuality, we're studying 3 nested pyramids. And we document this geometry through trigonometry rather than rounded numbers. We keep a parametric approach as long as possible because changes are bound to happen and the complexity only increases over time. So the clean 90-foot dimension of the outer face of the pyramid applies to the outer face of structure, which aligns over the foundation. So as we then move on to consider facade module sizing, we're 3-dimensionally offsetting from around 90-foot dimension and maintaining these formulas to guide sizing through to the end of construction documents. So that's the actual dimensions that we list on our drawings rather than saying 90 feet in a 64 or whatever. You have to keep it this precise. And that's how ultimately when you build a project like the Swatch headquarters, you get down to 0.1 millimeter precision tolerance. In parallel, we're working with our fabricators right from the outset of the project. So here again, we're working with Spearhead to optimize sheet material layouts to minimize waste. And we're also considering maximal transportable lanes. In addition to member sizing, our structural engineers also contribute to the assembly sequencing, which also includes site staging and maintaining the structural integrity of each face as it's craned into place. So we'll conclude with an animation of this project. So at the conclusion of this talk, I hope a few key points resonate. First is that across the spectrum from simple plywood houses to complex grid shells, wood presents a great breadth of possibilities in the face of constraint. And second, appropriate material selection and application is a critical factor in our efforts to build responsibly and reduce carbon emissions. That doesn't mean that wood is always the answer or that more wood is inherently better. Lastly, this is a highly collaborative field. Architects don't work in isolation, and the relationships that we build with engineers, fabricators, and builders carry from one project to the next and evolve a collective body of work. Prior to the publication of our timber book, Shigeru Ban was the only person in the world who knew all of these details. So as an office, we collectively believe that the best way to advance this discipline is to continue to collaborate and share our respective knowledge and experience. Thank you.
Thank you, Laura. That's what an incredible array of work, and thank you for taking us kind of deep on some of those projects. I full disclaimer, I moderated a talk with Laura at the Center for Architecture a couple of months ago, so I have a ton of questions from that. I also have some questions that I had asked Shigeru the other night that he chose not to answer. But I think maybe I'll just start by saying it's been a while since I felt that at the school, there's kind of been a theme or something that's resonated across many studios, programming. Ben's doing a timber studio, you guys are doing a mass timber studio. We have a beautiful exhibition in the hallway. I know in the third year, and we take on mass timber in the housing. I think it is that he's one or two of the structures. So it does seem like there's definitely something in the ether. And I just want to ask you, knowing what you know about the school right now, having gone through convocation and seeing kind of presentation on everything. What could or should we be doing pedagogically to advance the discourse in mass timber, to kind of prepare our students and young architects to kind of embrace this really convergent trajectory in this field? So I don't know what you think.
I think what's happening this semester is fantastic, and you're unlikely to find it in a lot of other schools in the Northeast. For those of you who aren't familiar, there are some mass timber degree programs in other parts of the country, particularly the Pacific Northwest, Arkansas, areas where you have a lot of state funding for forestry, and this drives the industry. It's a lot harder to find schools that are engaging with these questions in the Northeast because we just don't have the same setup. So to have 3 courses in a single semester in small school is fantastic from my perspective. I think continuing to engage with real world concerns, sometimes in a studio context, it's all hypothetical. You don't have a real budget or building code necessarily. As you start to introduce those real world factors, it allows you to design in a much more creative way rather than having a purely sky's the limit approach. And so I've really enjoyed that with our studio so far. I'd also say from my end, I know when I get a new project brief, what I can consider, I know what's possible, and the things that you can study in school are out of the realm of the everyday. So I've been very pleasantly surprised by the ideas our students have come up with in studio. I think it's really important to test these ideas when you're in an academic environment, because sometimes reality gets in the way in practice.
I mean, obviously the office has been doing this. I mean, Shigeru is way ahead of the game, right? You guys have been doing this, turned up on you personally, but the studio has been doing it since the 80s. And I think a lot of it has to do with his incredible kind of innovation and capacity to understand structural principles, and he's just understanding structures. And I think it came up the other night where even when he was at Cooper, he was kind of schooling his classmates and some of these things. Can you say something a little bit more about his unique relationship with the structural engineer and what that process is? That's what I try to understand.
Yeah.
It seems like something that's really special and specific, and because of that relationship can yield these types of projects, because a lot of architects are dealing with mass timber. No one really at this scale of innovation, Frank. So,
yeah, I would say as a starting point, if you look at any of Shigeru's sketches, he's sketching approximate member sizes, and then our structural engineers come in and say, well, that's basically right. What do you want me to do here? Shigeru innately has a wonderful structural sensibility. But in working with structural engineers like Hermann Blumer, Shigeru, who is, a world-class architect, he could be completely full of himself, but he's actually a very humble individual. He is very deferential to Hermann Blumer. He calls him Mr. Blumer. We all call him Mr. Blumer in the office. And it's a very beautiful relationship. Most architects hire another architect to write the foreword of their book, and he asked Hermann Blumer because he facilitates Shigeru's vision. So while the design concept always does come from Shigeru, it comes to fruition through collaboration with these phenomenal structural engineers and fabricators.
Maybe just because you ended on some of the drawings, some of the projects, which is, I think in the book it mentioned something around, was it the Swatch project that was actually built from a parametric model that didn't have a typical or traditional set of design documents? How have your kind of modes of representation, instruments of service kind of changed and adapted to some of these projects? Because they seem like you need a whole different language to be able to explain really thoughts.
Yeah, I would say, again, it's just being able to collaborate with really talented consultants and all have the same project vision in mind. For the Swatch project, we worked with a digital facilitator called Design to Production. If you're at all interested in parametric modeling, I highly recommend looking them up. The head of their firm is called Fabian Schur. He has fantastic YouTube videos that talk through exactly how they approach the work. And so their role was to do conflict detection for any of the sprinkler pipes, et cetera, passing through the timber structure. On our end, I didn't work on that project. It was out of our Paris office. But we typically work with Rhino models. It's not anything, unfamiliar. And then we pass this back and forth with our structural engineers, with our fabricators. They often have their own proprietary software for coordination. But primarily we're working with CAD and Rhino, not anything, unusual. Typically, we aren't working with Revit because these aren't conventional repetitive structures.
We can open it up to him.
Oh, thank you so much for the lecture. It was really informative. I guess my question isn't about any of the projects, but just as a general kind of question about mass timber. How would you address the concerns that the quality of timber in general is getting poorer throughout the years. Like, I've seen a lot of images on the internet that say you took a cross section of a 2x4 40 years ago and a 2x4 now that's available for purchase at like Home Depot. It's drastically different quality. Would you say that you found faced difficulties within your field related to the timber quality?
No, that hasn't come up. Timber is graded both for its defects and its aesthetic appearance. So from our end, as architects and working with our structural engineers, we have certain minimum criteria that have to be met in the material that's supplied to us. But yeah, not directly. I am aware of what you're talking about, but those materials, if they are subpar, just wouldn't be considered for a building. But overall, it hasn't affected overall member sizing, for example. It's not that everything needs to be thicker to address changes in wood.
My question is, does it happen often that you have to prove to the officials that would have a certain type of stability? For example, you show that Shigeru Ban tested the fire proofing of the plywood to the Japanese officials. And especially when the firm is working across the globe with different governments with different acceptance as a material.
Yeah, it really does vary around the world. So there's performance-based code and then there's prescriptive code. So if you're following the prescriptive code, you just follow the letter of the law and build what's allowable. If a particular jurisdiction allows for performance-based testing, you can demonstrate like those fire tests, like the stress test of the Baltic birch plywood. It really depends on the jurisdiction, and sometimes it depends on competing lobbies or whether the fire department in a local jurisdiction will even tolerate the consideration of mass timber buildings. So here in New York, we've seen a great change over the past decade, but none of these projects are in New York City. Now it's more possible.
Question about the units, different units, because you guys work across the globe, right?
Mm-hmm.
Swiss manufacturers, they have in Canada,
Mm-hmm.
and in terms of like inches versus millimeters, like you guys have to constantly convert, or in the very beginning you kind of just say, well, let's work on one unit for this project?
Yeah, we always just work with the units that are local to a project. And so I predominantly work on US and Canadian projects, but if I'm working on a project elsewhere in the world, it's automatically metric most of the time.
And the manufacturer will match their units with where the project's being happened.
So our fabricator will, and so a lot of times that's because you're considering like locally supplied hardware. So it is a good point. You don't want to be designing just in the unit of measure that's familiar and comfortable. So you pick what the local jurisdiction would do.
I was wondering at what stage you guys determine like specific connections like between the two members. Like, is it during the mathematical calculation kind of phase with the engineers, or is it after those iterative modeling tests?
We usually design it at the outset. So for a typical SBA project, we have a phase called concept design that we do before we get into schematic design development, et cetera. We're typically designing those joints right at the outset of the project, and it actually comes up in Shigeru's initial sketches. And then it's more a question of how to fabricate it that comes later. Sometimes those joints do need to be reconsidered as we get into greater detail.
In the very beginning, you showed a diagram with the carbon emissions of wood compared to, I think, concrete and steel. I was wondering how that compares with, I guess, a normal unaltered piece of wood to what you guys are doing, like the parametric designs and all this manipulation that comes after, and the carbon emissions from that kind of process that wasn't really mentioned in that initial.
Yeah, it's a good point, because I think when you're doing a quick slide, you can't capture all of the realities of carbon accounting, because if we just say wood performs twice as well as steel and concrete, well, then you have the question of like, how do you transport the wood to site? Is it coming from Austria, which is currently one of the cheapest sources of wood and then being trucked and shipped over to the US, well, you've just blown your carbon argument out the window. So as you consider a diagram like that, you still have to consider the material efficiency of how you're laying out your material. So if it's being cut from a single piece, how do you maximize the sheet layout? For anything that's parametrically modeled, the swatch project is not particularly wasteful because they were able to nest all of the curvature in the source wood. But those are factors that have to be baked into a carbon calculation.
I actually had a similar question to my classmate Caroline about your process when it comes to certain infections that you're looking at. And I think whether we want very if it had any certain type of hardness wood or if there's any or knots within the wood from items.
Yeah. So one interesting thing that you'll see in Shigeru Ban Architects work that doesn't come up quite as often in other architects' work with mass timber is the use of hardwood for those more innovative joints. So if you happen to be at Shigeru's lecture, he talked about the Tamedia building project, which had these oblong posts for joints, and those were made of a hardwood, whereas the rest of the structure was a softwood. So oftentimes we'll use a hardwood pin at a joint to take on those greater stresses. Sorry, did I address all of your question? What was the rest of it? Yeah, that's okay.
I had a question about mainly the kind of similar to like the Swatch building, and you were referencing lightness in the Omega building and how you guys got to combat that the ground. And I was just really curious, especially with the rise of like more destructive climate phenomena, how the roofing in respects to these mass timber structures, how is that addressed, the lightness of it, and how is that reinforced?
You mean like just preventing uplift?
Yeah, just preventing anything from like collapsing and
I mean, overall, just collapsing. It's that isn't an issue. Everything is kind of tied back to the core in that case. The roof of, trying to think, the roof for both the Omega factory and the Cité du Temple building, they're both kind of conventional structures. So if you're talking about the lightness of the wood structure, it's usually in the wood floors themselves that are more of a concern. The roof is not solid wood.
Yeah, thanks. I have a long question.
Go for it.
Yeah, so I'm struck by the evolution of your firm and the development of your firm and what seems to be a shift in maybe in intention or focus, but maybe not. And I thought it came out really strongly in the kind of pairing of the Omega project with the Swatch project, where there was something that felt very old school, kind of Shigeru Ban, even pre-paper tube Shigeru Ban, in terms of its incredible reductive and more formally driven approach to making space and having a structure that is certainly significant to the reading of that formal space, but not necessarily, kind of in a potentially more decorative way, taking over the reading of the space. So there was that one, and then the Swatch, where I found two things going on. One being definitely a much higher level of decorative quality to the structure itself, but also what was oddly what seemed to be an obsession with precision. So it's precise to 0.1 millimeter tolerance, but I guess I would have to ask, why is that significant? And in a construction project where, we miss by 1 we miss by 1/10 of a millimeter everywhere you look, or certainly in terms of U.S. production. Maybe it's just our construction detail, but why is precision a value that would drive sort of design and effort and that kind of thing in the structure. And I wasn't sure if you said something about, every panel fit, and if there was a tremendous number of panels or if they were all the same panel. And yeah, so there were many different panels.
Panels.
So here's in some ways a like kind of an interest in how far can you push the complexity of the structure.
Mm-hmm.
And I guess an interest in that as a value. So I guess I'm partly curious about why is that a value, especially with a material which is when it's used in less well-funded structures, folks who are trying to do mass timber projects in the US seem to be plagued by the dilemma of mass timber having a tremendous amount of movement as it goes through heating and cooling cycles and also wet and dry cycles. So there's kind of giant tolerances that have to be built into the structure and really complex connection details so that the structure can move to the degree it needs to. So I was kind of saying where is like mass timber as an evolving material and an architect and the architect's interest in it, if on the one hand there's a search for 0.1 millimeter precision, in other ways the material needs to have big tolerances like a half an inch, a quarter of an inch, that will allow the structure to move because of its apparent material qualities. So, and then there's an attention to formal considerations and attention to, I don't know what word to use, maybe a more animate surface rather than a more decorative surface, but certainly something that is not trying to kind of clarify a reading, but it's seeking a much more complex read.
Okay, if I miss half your question, remind me. I'm not trying to evade it.
It's just I found myself struck by this kind of really interesting evolution of images. And then if you want to take another one on, just while you're at it.
Can I get the first two first?
Sure.
Okay. So it's a common joke among structural engineers and fabricators. If you smell sawdust on a mass timber site, somebody's done something wrong. You design to that high level of precision because you want the members to come into place, slot exactly where they need to. This saves time, this saves money, and this saves material by not needing to refabricate things. So as we try to fabricate as much as possible offsite, you want to just come in and have a very quick assembly. In terms of the tolerances, when you have a long structure like the Swatch headquarters, if you start to bake in more than that 0.1 millimeter, by the time you get to the end of the structure, it really depends, well, which end of the building did you start constructing it from? And that Swatch headquarters, I'm just gonna see if I can go back to that. It actually sits on its neighboring building. There we go. So if the structure had been off by the time you get to the end of the Swatch building, it's then going to be putting pressures not centered on the columns of the adjacent building. There's also the beautiful situation that like we can go to that level of precision. So why would you round?
Yeah, no, I think for me it was that, but what do you do with the fact that the material needs a lot of room to move?
Oh, you design to be at the middle of that range so that it can shrink and expand, and you are still fitting perfectly in the joint so that it can shrink and expand together rather than being at the far end of that time. And I didn't mean that to be snarky. It's just the way that the parametric models work, you can keep it in this formulaic approach rather than saying, oh, we're going to round to the nearest quarter of an inch or 32nd. And everyone gets really frustrated in drawings when everything's rounding to the nearest 64th and not being a clean number, but you kind of have to keep it in those terms. A lot of times we'll draw and we'll keep it to the rounded numbers, but have this separate parametric model that's kind of the overarching reference geometry model. Then to address your question about kind of the shift in architectural style, so to speak, not every project is the Swatch headquarters. this project is about 5 years old now. The Kentucky Owl project also has a degree of structural exuberance, but the majority of our projects are not going to be that because there just aren't that many projects in the world that can support that budget, that level of great open public space that gets to be, having these beautiful, innovative, long span structures. I think Shigeru tailors his aesthetic approach to the needs of each particular project. And so having a watchmaking workshop, for example, be this kind of staid, quiet aesthetic, it's fitting to the needs of the project, whereas swatch is supposed to be playful. And so that's why it appears the way that it does. In terms of fabrication and the idea of like mass customization versus the use of repetitive members, we are more often on the side of using repeated structural members. So I'm working on a residential project right now. We have bent glulam beams. We have one radius for the entire house, and then it's just cut to different lengths. So sometimes you have a complete half circle. Sometimes you just have a portion of an arc, but it's all in the name of fabrication efficiency of keeping that same standardized radius. So it really just depends on the project. This is a perfect confluence of high Swiss standards fabricated in Switzerland with Swiss structural engineers.
And Swiss wood.
And Swiss wood, yeah.
Or Swiss watch.
Or Swiss watch. And then at the end, you can say it's built like a Swiss watch, and everyone laughs.
I mean, just to build up that, I think it is an interesting question. Like, well, why do you need this kind of a superhuman level of control? And the answer is in the watch. I mean, the mega watches can keep time for millennia. And do you need that to, get to your meeting on time? Like, probably not. But I think the evolution of that grid of images that Elizabeth talks about is so interesting. Like, I don't know if you can go back to the very last image, but it also kind of tracks basically the kind of evolution of, a number of things simultaneously. Like the mass timber industry kind of evolves from top left to bottom right.
Right.
I mean, so does the kind of parametric tools that are necessary or evolved with that industry. And I think there's another kind of interest emerging, I think, for in the wood world, and that is not just. And I'd like you to kind of maybe remark on this, but like not just the production of, let's say, mass customized parts to produce. And I know you're also interested in modulated parts, but not just to produce standard parts, whether they're mass customized different parts or modulated parts, but rather to, like what's in the hallway now, but is to look at wood as a non-standard part and to look at its native attributes as a tree as something non-standard. And if this evolution is pointing in a direction to deal with like a non-standard tree as a part, is there, are you interested in what that might offer?
Yeah, on a personal level, absolutely. And that's something that we're having a lot of fun with in studio. We've been talking in particular, there's one tree species called the black wattle tree that has an irregular growth pattern. We've been talking about if you're approaching mass timber and that species doesn't lend itself to boards and beams, how could you start to think about use of smaller strand lengths to make composite materials? How could you start to think about producing mass timber in mobile manufacturing setups that are adjacent to a site rather than saying, oh, well, your only mass timber manufacturers are in certain locations and you're shipping halfway across a continent just to build a project. I completely agree. It's a really interesting area. As we engage with projects, it's always a question of time and cost to engage with these innovative approaches. And a lot of the times, Shigeru does pursue those innovative approaches and testing to demonstrate work with that. We haven't I have to make sure I'm not missing something here. We haven't really pioneered a new species in mass timber. Shigeru did develop a material called laminated bamboo lumber. So going back to the furniture house project, there's a whole furniture house series. The fifth one was in China, and it was very hard to find plywood locally, but he found these laminated bamboo mats. And so he took those back and studied them and then proposed using bamboo sheets to make plywood out of it. And so he has engaged with alternative materials in that way, but we're all familiar with bamboo. I've rambled a bit off if I am getting your topic. Yeah, and so in terms of standardization of mass timber versus the individuality of a tree, it's exactly the standardization that allows us to build prolifically in mass timber in multi-story configurations and have confidence in the wood that every member will meet a minimum standard. And so whole tree construction is super interesting. It isn't something that we've delved into, but it's certainly beautiful. And I think now that, more of the world is recognizing the importance of forest health and trees and wood, I think you'll see more of that. And I hope you'll see more of that.
Yeah, it reminds me of, not to ask me, but it's kind of like cooking. There are more ingredients that you can use from a tree, and that mass timber, it shifts the focus to certain species and certain parts of trees of certain species. But there's a lot left on the table for consideration.
Well, and I think architects like Michael Green are asking good questions about what do you do with these wood byproducts? How can you make alternative materials from those short fibers and what's left?
Yeah. A lot of traditional wooden architecture has the ability to shift and kind of absorb earthquake resistance. And a lot of these parametric structures we see are very complex in their geometry and very precise, as you mentioned. So I'm beginning to wonder, is there any project that has been kind of designed parametrically using those vernacular principles to be susceptible to earthquakes?
So fortunately, Japanese architecture has a long lineage of dealing with timber structures and movement in relation to earthquakes. The feature of timber structures lends itself to being resilient in those situations. If you look in the bottom right, you can see that the notches in that beam are actually wedge shaped to accommodate the wood movement in the joint. And so that's designed into the parametric model and then fabricated right into the project from the outset, even though we wouldn't expect a massive earthquake in central Switzerland.
Thanks for that. I'm not sure if you're the person to answer this, because it seems like your focus is really on mass timber. But I'm just going to ask you anyway, because like last week this question was being answered with a no. It's similar to this question about tolerance versus precision, and then like in this project you said you provide the tolerance there. But I see a detachment between this kind of mass timber project and the big one in terms of tolerance required, in terms of the design of joinery. Like for example, no one would screw the plywood from the side, but that's what the people lockouts is. And then also you were saying like in this mass timber project you always work with professionals, but like what Hayley said last week, the paper lockhouses built in places of disasters. And even we as Cooper students who of available equipment, and we CNC the plywood, we're still failed to put them together smoothly. So I can't imagine how it was actually like in a more in a less ideal site, in a less ideal situation. So why is there such disconnection between these two sides of design construction and the consideration of material of the Shigeru Ban Architects?
I mean, going back to your comment of it being a failure to address that level of precision, I think a term like that is specific to an individual's assessment. I wouldn't consider it a failure. I think also, if you're in a disaster relief circumstance where you just need shelter, you're not going to be as concerned with is something an 89.9 degree angle or 90 degree. You just want to keep the weather out. The project that was fabricated for the glass house was an exhibition version. And so it is kind of the pristine, clean presentation version of a project, which is different from something that's being built in the field by, again, students and local workers and people who aren't trained construction workers. So, I mean, I think everyone did a beautiful job with the paper log house, and it's wonderful to see up at the glass house. It is hard to learn how to fabricate things, whether it's a paper log house or if you are a first time builder of a mass timber project. So there is a learning curve on any of these things. Typically in disaster relief context, we have someone from the office who has built many of these projects all around the world, leading the students, and that's certainly helpful to have that kind of guidance. In terms of precision, I'm not sure if I understand the disconnect that you're pointing to on the paper log house end versus the mass timber complexity end. But I think there is an ideal, so to speak, that's attempted in all of these projects. And sometimes the criteria for evaluating that is different. Did I answer your question?
When I say fail to assemble, that means like, so let me just give an example. So there are joineries of the paper log that's assembled by pieces of plywood in a box. So then you need to like put the paper tube onto that box thing, and then you drill on the side, drill the screw into the side of the plywood. So this process always the thickness of plywood is only like half an inch. So this always results in like breaking the plywood because we drill it from the side. This is just one of the examples of like, I'm saying like the consideration of the tolerance is not enough to put this project in a smooth. And that was like under the situation when we have all the that's what I'm trying to say about failing to assemble. We failed to construct it, we did, but we had to change things, we had to send things a lot. So yeah, there are a bunch of solves.
A lot of trauma and a lot of
And I mean, if you're actually on site and something doesn't fit together, and again, you're just trying to keep the rain out, maybe the building ends up being a half inch shorter than it needs to be just to get the job done. You can't always start over with fresh materials because that's a waste. A lot of the materials that would be used, if you try to use local materials as much as possible, if something has to be fabricated and shipped in, that's not as efficient. Things can get lost and held up. So I have not been on the ground for any of these disaster relief reconstruction projects, but somehow they do get it done.
Final. Thank you, Laura. That was really impressive.